In our physics lesson today, we are going to look at magnetic field patterns, how the magnetic field lines arrange themselves. And we have the first statement there. Draw the magnetic field patterns for a bar magnet. So our first diagram is showing how the magnetic field lines are spread in a bar magnet. We know a bar magnet has north and south. So one of the properties of magnetic field lines of force says that the lines of force start from the north and they go to the south. So you can see these ones are moving from north, the arrow, and they go to the south. This one is also moving from the north and is going to the south. Then we said in the middle there should be straight lines, and inside the magnet no field line passes through the inside the magnet. So this is a magnetic field line, or magnetic field pattern rather, for a bar magnet. The arrows should be leaving from the north but entering at the south. Then we have part B for a single north pole. Single means one. So there is only one north pole, the south pole is not there. So what you do, you just draw a circle, put your capital N there to mean the north pole, and then you draw the field lines going out. Remember, we are saying from the north they are leaving, so you can see they are all leaving. Then the opposite is for a single south pole. The same diagram but with the S, and then the arrows should be entering. This one has a mistake, so you can correct it. You see, they should all be entering like that. Then we have another case where you have two bar magnets with opposite poles near each other. So we have here two bar magnets. This is one and this is the next one. North and south, that is one bar magnet. North and south, that's another bar magnet. But here the north pole is brought near the south pole. So the examiner is interested in these two poles which have been brought near, and the statement says opposite. So opposite means north and south. Now, this diagram and this one, they are just the same. Only that here, the north is this side and the south is this side. But here, the north has been replaced by the south, and then the south has been replaced by the north. So we all know that from the law of magnetism, which states that unlike poles attract. So we expect these ones to attract. And how do we show that they attract? By drawing the magnetic field lines connecting north to south. In the middle, it is a straight line. Then we have the other ones are in form of curves, but the arrows should be moving from north to south. Now, when you come here, it is the opposite. The north is this side and the south is this side. We have the same diagram, but the arrows change because the north has changed from north to south. Then when we move to another, that is part E, two bar magnets with similar poles close to each other. Similar means the poles are the same, or they are like. So like means north near north. So what happens? They repel. How do you show that they repel? You see these arrows move from north and they go towards what? The south. All of them, these ones are moving from north, they are going to the south. These ones are also moving from north, going to the south. The same story here, from north to the south, from north to the south. So there is going to be an area here where the magnetic field lines will not pass, and we are representing that area by letter X, and we are saying that X means a neutral point. Neutral because no field line passes there. So this is north and north brought near each other. Then when you come here, you have south and south. still the diagram looks the same. It is only the arrows, because we are saying at the south they should be entering. You see, they are all entering, but at the north they are all what? Leaving, by the same diagram. And in this case, there is also going to be a neutral point which is created here. Okay, then there is another case, you see, where you have two parallel bar magnets with their unlike poles near each other. You see, the magnets have unlike poles near each other. North near the south, south near the north, near the south, and then south near the north, but they are parallel. So when you are drawing them, you make sure that the magnets are parallel. Parallel means they could be parallel vertically, the way we have drawn, or they could even be parallel horizontally. Now, what happens here? Without this magnet, the magnetic field of this one is from north, you see, coming here to south. You have north coming here to south. Then when this one is also not there, this one also will be from north. North is down, so the arrow will be going up. From down going to be going up. Then you have also to give the connection between this north and this south. So the north is here, so you draw another one starting from here, going to the south, from north going to the south. Then you also draw another one connecting the neighbors now, from north to the south. And that is the same thing which happens this side. The only difference here is, here they are unlike poles, so they what? They attract. But here they are like poles. You see, like north near north, and then south near south. How do you show that they repel? By drawing. When this, you see, from north, first of all, without this magnet, this one has north coming to south. You have another one here, north coming to south. This one also from north coming to south. This is north coming to south. Then you have another one. When this one tries to move and this one also tries to move, because they are the same, the relationship between this one and this one. So what happens? They repel. So they try to bend away and they create a neutral point. And the same thing also happens down here. This one tries to come, this one tries to come, but they cannot what? Attract. So they end up what? Repelling. And what did we say? That at the south they are entering. You see, they are entering because this is south. Then at the north they are leaving. So these are two bar magnets with the north poles close to each other. See? But here you have two bar magnets with the opposite poles close to each other. So here we expect attraction throughout. Here we expect attraction between the north and south, then repulsion between the south and south, and then south and south. So our diagram looks like that. And for that reason, because there is a repulsion here, we have a neutral point created there, a neutral point created there. And we are saying X represents a neutral point. Now, what about if it is a horseshoe magnet? How does a horseshoe magnet look like? This is the diagram of a horseshoe magnet, you see, like this. So you have one side north, since it is a magnet, one side is what? South. The north can be either here or up, anywhere, as long as there is one side north, one side what? South. In our case, the north is down and the south is up. So we expect them to attract. So how do you show that they are attracting? You see, you make these curves, these connections, and the arrows should be from the north to south, all of them leaving the north but going to the what? The south. So at the south they are entering, but at the north they are leaving. So we are saying this is a horseshoe magnet. Then we have another term. There are two terms actually which we need to define. Magnetic field line of force. These lines here, these ones, these are magnetic field lines of force. So by looking at the way the magnetic field lines of force, they move from north, they come to the south. So it means as if it is the north pole moving, because the movement starts from north going to what? To south. So we define a magnetic field line of force as a route or a path along which a free north pole would move if free to do so. What does that mean? If that north pole was very free, it would move like that. It would move from here and come like this. So it is a path along which a free north pole would move if it is free to do so. A path, it is a path along which a free north pole would move if free to do so. Then we have this area which we are calling the neutral point. What do we mean by a neutral point? Now, a neutral point is a point, as the word says, where, or you can say at which, the resultant magnetic flux density is zero. Yesterday we said the magnetic flux is actually a group of magnetic field lines. But when you look at this diagram, here there is no magnetic field lines which passes. So the flux density is zero. So you define a neutral point as a point at which the resultant magnetic flux density is zero. Let's have a short commercial break, then we come back. Okay, now we are looking at an experiment to determine the magnetic field lines of force. So the question is, describe an experiment to determine the magnetic field lines of force. What does that mean? We are saying the magnetic field lines of force move from north and they go towards what? The south. So there should have been an experiment carried out to find out that the magnetic field line of force moves from north to south. And here we are going to have an experiment. In this experiment, we need a bar magnet, and we also need a beaker. So we have a bar magnet